My name is Manuel Camarda and my innovative master thesis is Model Predictive Control for Energy Saving of Hybrid Trains in Catenary-free Scenarios. I decided to research on hybrid trains for three reasons. First, my hybrid train can reduce the reliance on overhead catenary wires, allowing operation both in electrified and catenary-free scenarios, greatly enhancing flexibility. Second, I aim to mitigate the environmental impact by incorporating renewable energy sources, like hydrogen fuel cells, which produce only water and heat as byproducts. Lastly, I want to increase the train's efficiency by minimizing losses. My work, using data provided by the industrial partner Alstom, started with the creation of a detailed electrical circuit representing the train functioning. It is constituted by three energy sources: the hydrogen fuel cell, the lithium-ion battery, which can also be recharged when regenerative braking capabilities are exploited, and the catenary, from which the train can detach. Then we have the auxiliary services, which comprise functions for passengers' comfort, the traction motor that moves the train, and lastly the connection line between the carriages. This model, however, is too complex to be used for real-time control implementation, so it needs to be simplified through the development of the control strategy. This is a model predictive control, MPC, with an economic cost, and the starting point is the definition of the states, the control inputs that are the fuel cell current, the battery current, and the catenary current, and lastly the disturbances. It is essential to define some constraints, especially for safety, so the system always operates in physical conditions. The central part of MPC is the cost function, which is designed to minimize losses related to Joule effects, while guaranteeing that the levels of the batteries and fuel cells remain within their optimal ranges. To assess my work, I considered two existing methodologies: a MPC realized for a hybrid train relying on catenary and batteries, and the heuristic, comparing them with my proposed approach. Considering the same route for all the strategies, this is the required traction current, where the green part corresponds to the catenary-free section. A noteworthy simulation is the one of the catenary and intercarriage currents. The proposed method strongly decreases the current drawn from the overhead line by 67% and 46% with respect to the other two strategies, leading to a reduction in the strain on the infrastructure. Also, the maximum intercarriage current is decreased by an impressive 84% and 75%. A visual representation of the losses at each time instant highlights the effectiveness of my work, which reduces them by 68% and 33%. In the end, the main results reached are decreased losses, increased efficiency, reliability, flexibility, and greater environmental sustainability. Thank you for your attention.